The universe is vast, an endless expanse of cosmic wonders, stretching far beyond our comprehension. It's a realm of swirling galaxies, radiant nebulas, and mysteries waiting to be unraveled. A tapestry of silent, glittering stars, each one a sun in its own right, possibly surrounded by planets we can only dream of. For centuries, we've looked up and wondered, are we alone in this grand cosmic theater? Is there anyone else out there gazing back at us, pondering the same questions? We've sent signals, broadcasting our presence into the void, hoping for a reply. We've listened for echoes, straining our ears for any sign of intelligent life amidst the static and noise of the universe. And we've searched, tirelessly, with our most advanced telescopes, for any sign of life in the cosmic ocean, peering into the depths of space and time. The silence can be overwhelming, a stark reminder of our place in the universe, making us feel small and isolated in the face of such immensity. But what if the universe has been speaking all along, not in radio waves or flashing lights, but in the very air of a distant world, in the subtle chemistry of an alien atmosphere? This is the story of K2-18b, a planet shrouded in mystery, a world unlike our own, a world orbiting a distant red dwarf star, 120 light-years away, glimpsed only through the lenses of our most powerful telescopes, a tiny speck of light holding immense potential. K2-18b isn't just another planet, it's special, a beacon of hope in our search for life beyond Earth. It promises secrets that could change everything we know about life, its origins, its possibilities, and our place in the cosmos, forever altering our understanding of the universe. 120 light-years away, a mystery is unfolding, a story written in the stars, waiting to be deciphered. A cosmic whisper we're just beginning to hear, a faint signal from a distant world that could hold the key to unlocking one of humanity's greatest questions. We search for water, the lifeblood of our planet, the universal solvent that makes life as we know it possible. We search for worlds not too hot or cold, nestled in the habitable zone of their stars, where liquid water can exist on the surface. We search for the building blocks of life, the organic molecules that could spark the genesis of new ecosystems. K2-18b seems to have it all, a tantalizing combination of factors that make it a prime candidate for habitability. A tantalizing clue in the greatest detective story ever told, a cosmic puzzle that has captivated scientists and dreamers alike. But every answer brings more questions, and every clue deepens the mystery, leading us down new paths of discovery and exploration. The data from this distant world is thrilling and perplexing, a complex tapestry of information that challenges our assumptions and forces us to confront the possibility that the answer to our oldest question is finally within reach. The story of K2-18b is, in many ways, our own story, a reflection of our hopes, our dreams, and our relentless pursuit of knowledge. Reflected back at us across an ocean of stars, a reminder that we are all connected, all part of the same cosmic story. Far beyond our solar system, countless worlds await discovery. Imagine a world 8 times more massive than Earth, a colossal sphere suspended in the inky blackness. This is K2-18b. It orbits a cool red dwarf star, a star significantly smaller and cooler than our own Sun, located in the constellation Leo. This exoplanet is nestled in the habitable zone, sometimes called the Goldilocks zone, where temperatures are just right for liquid water to exist on its surface. But K2-18b isn't rocky like Earth. Instead, it's likely a Hycean world, a fascinating type of exoplanet. This means it's an ocean planet almost entirely covered in water, with a thick, hydrogen-rich atmosphere enveloping it. Picture an endless ocean stretching in every direction, with no continents or land masses to break the monotony, all shrouded in a dense, hazy atmosphere. It's an environment unlike anything we've ever encountered in our own solar system, a truly alien landscape. The existence of Hycean worlds challenges our traditional definition of habitability, significantly expanding the possibilities for where life might exist in the universe. What truly sets K2-18b apart from other exoplanets is the composition of its atmosphere, a key factor in determining its potential for life. Through careful observations using powerful telescopes, scientists have revealed the presence of water vapor in its atmosphere, as well as methane and even carbon dioxide, gases that, on Earth, are intrinsically linked to both biological processes and geological activity. These groundbreaking findings painted a picture of a complex and dynamic atmosphere, a planetary-scale chemical laboratory where countless reactions might be taking place. Its unique size, its strategic position within the habitable zone, and its intriguing atmospheric composition have made K2-18b a prime target for observation by our most advanced observatories, like the James Webb Space Telescope. But then, in a stunning turn of events, scientists analyzing the data discovered something even more intriguing, something that could change everything we thought we knew about the potential for life beyond Earth. Hidden deep within the complex atmospheric data was evidence of a specific molecule, one that is almost exclusively produced by living organisms here on Earth. The implications of its discovery sent shockwaves of excitement and cautious optimism through the entire scientific community. The mystery surrounding K2-18b was about to deepen, leading us into uncharted territory in our quest to understand the universe and our place within it. What could the presence of this molecule mean for the search for life beyond our planet? The molecule at the heart of this story, the one that has scientists buzzing with excitement, is dimethyl sulfide, or DMS, a compound with a surprisingly potent connection to life as we know it. On Earth, DMS is responsible for giving the ocean its distinctive briny scent, that familiar aroma we associate with the sea. And here's the crucial part: DMS is produced almost entirely by life, specifically by phytoplankton, those microscopic powerhouses of the marine world. These tiny marine organisms release DMS as a natural byproduct of their life cycle, making it not just a component of the ocean's smell, but a key part of our planet's sulfur cycle, a vital biogeochemical process. So the potential discovery of DMS on K2-18b, a planet light-years away, is electrifying the scientific community, because in the context of exoplanet research, DMS is not just any molecule. Here it's considered a strong biosignature, a potential indicator of life. Unlike water or methane, which can be created by a variety of non-biological geological processes, DMS is considered a much more specific fingerprint of life, a compound that's harder to explain without the presence of living organisms. Its presence, especially when considered alongside the absence of other expected chemicals like ammonia, which might be consumed by biological processes, significantly strengthens the case for the possibility of biology at play on this distant world. Scientists are now actively theorizing that a biological process, perhaps similar to what we see with phytoplankton on Earth, could be consuming ammonia on K2-18b, further hinting at the possibility of a dynamic, potentially living world far beyond our own. Finding DMS on another planet is akin to discovering a message in a bottle, carried across the cosmic ocean from an alien world. It's a complex puzzle, and the detection of DMS provides a crucial piece that, when assembled with other data, points towards the tantalizing possibility of life. If confirmed through further observations and research, this would undoubtedly be one of the most significant discoveries in the ongoing search for extraterrestrial life, a monumental leap in our understanding of the universe. But the question remains, how did we manage to detect such a faint and distant signal from so incredibly far away, across the vast expanse of space? Detecting a molecule in the air of a planet 120 light-years away requires extraordinary technology, the James Webb Space Telescope. Webb's giant mirror captures faint infrared light, acting as both a time machine and a chemical sniffer. Using transmission spectroscopy, Webb observes starlight passing through a planet's atmosphere during a transit. Molecules absorb specific wavelengths, creating a chemical barcode in the light. By comparing starlight before, during, and after a transit, astronomers identify which gases are present. The process is delicate, like spotting a firefly next to a searchlight from miles away. Webb's sensitivity allowed scientists to gather enough data over multiple transits. Within this data, the signature of DMS appeared, a tentative but thrilling detection. This achievement pushed the telescope to its limits and marked a new era in exoplanet science. We're no longer just finding planets, we're reading the stories written in their skies. But what does this chemical whisper truly mean? The possible discovery of DMS on K2-18b raises the ultimate question: have we found evidence of alien life? If confirmed, it suggests a vast ocean teeming with life, shaping the planet's atmosphere. This would be a paradigm shift, the first concrete sign that life isn't unique to Earth. A Hycean world's life would be profoundly alien, adapted to a hydrogen sky and a red dwarf's light. Yet, it might have evolved similar biochemical solutions, like producing DMS. The implications are monumental. Certain biological pathways could be common across the galaxy. We're not talking about advanced civilizations, but microbial life, the unseen foundation of ecosystems. On a planetary scale, microbes can transform worlds. The discovery of DMS could be our first glimpse of an alien biosphere, but extraordinary claims require extraordinary evidence. The prospect of life on K2-18b is exhilarating, but science demands skepticism. The detection of DMS is tentative, the signal is weak and needs confirmation. Webb will need to observe K2-18b again to strengthen the case. Even if DMS is confirmed, could it be made by non-living processes? Scientists are exploring exotic geochemical and photochemical pathways unique to high-sea worlds. K2-18b's ocean might be too hot, or its atmosphere too dense for life as we know it. It may not even have a solid surface, just a dense atmosphere fading into a liquid or icy core. These uncertainties define the scientific process. The mystery is complex, but the search itself is a profound journey. Whether the answer is life or exotic chemistry, we'll learn something fundamental about the universe. To move from possible detection to confirmed discovery, scientists need more data. The initial findings came from just 2 Webb transits. More observations are underway. A stronger signal would boost confidence in the presence of DMS. But confirming DMS is only half the battle. Scientists must rule out non-biological sources. Laboratory experiments and computer models will simulate K2-18b's conditions, testing if DMS can form without life. Only by exhausting all possibilities can we build a strong case for biology. The gold standard is finding multiple, independent biosignatures, like other complex organic molecules. We're searching for a pattern of chemical clues that all point to life. The burden of proof is immense, but the stakes couldn't be higher. K2-18b is just one of many worlds in the search for life. The universe is filled with potential homes. Thousands of exoplanets discovered by Kepler and now studied by Webb. Systems like TRAPPIST-1, with several Earth-sized planets in the habitable zone, are prime targets. Closer worlds like Proxima Centauri b and other super-Earths await investigation. We're moving from counting planets to characterizing their atmospheres and environments. The search extends beyond planets. Moons like Europa and Enceladus in our solar system may also harbor life. If life exists in such places here, perhaps similar moons orbiting distant giants could be habitable too. The search for life is a search for niches, environments where the right ingredients come together. K2-18b shows us that these niches may be more exotic than we ever imagined. We stand on the brink of a new age of discovery. The mystery of K2-18b pushes the boundaries of science and our sense of place in the cosmos. Whether we find a living ocean or a strange natural process, the outcome will be revolutionary. We'll learn where the line between chemistry and biology truly lies. The search for life is a mirror reflecting our deepest hopes and fears. Even finding microbial life would transform our perspective forever. It would mean life is not a miracle unique to Earth, but a common outcome of the universe. Yet it would raise new questions. Where are the civilizations? Why is the universe so quiet? The search for life is a search for meaning, a quest to understand our own reflection in the cosmic mirror. Whatever the answer, it will change humanity forever.